to the last lecture of our week of water and the sewage treatment. Today, I have the honor to introduce Stuart Wakefield, Original Manager from Malvern Panalytical. Stuart supported the Israeli market for more than 20 years, right?
Yeah, that's correct, yes.
And today we are talking about real-time chemical dosing optimization in water treatment. We also have Yael Shaked here. Yael is the manager of the biophysical characterization in materials in Dr. Golik. Thank you for attending, and now I'm gonna share you with Stuart with you. Let's do it.
Okay, thank you. So everybody can see my screen, I hope. Just a quick check. I'm assuming yes, as nobody has come back and said no. So good morning, everybody, or perhaps good afternoon if it's 1 minute past midday now. So today we're going to talk about real-time dosing optimization in water treatment. We'll talk a little bit about the background, the technologies that are implemented or deployed in that area, along with some different ways to approach it. And perhaps more interestingly for people, we've got some real examples from the end that is taken from data from actual water treatment plants shared by those companies from their PLC systems, with some details about financial savings, about improving dosing optimization into their plants. So generally speaking, for the water treatment industry, the quality of water is just not negotiable. Okay, we are in a position where if we're not delivering quality water, we are, potentially causing huge problems to the population, it affecting people's health, and so on. And as a result of that, typically what happens is that the water treatment industries spend more than they perhaps need to meet these quality requirements. But at the same time as meeting these regulatory standards, they also have to try and drive down the costs. We can't just keep on top of these things and providing overkill in terms of too much chemical just to make sure we're okay. And the first step in most of the processes of these water treatments is typically adding chemicals to aid in clarification. So that the flocculation of the suspended organic material to flocculate it prior to sedimentation techniques in your process, or direct filtration, depending upon what your process is. So very often, a lot of people say that, we don't want to have too much sludge production, but often that is preferable, and they will spend more on chemicals to stop that. And one of the things that we have to understand is overdosing or overcompensating very often can restabilize the suspended particles. Okay, so, and it can decrease efficiency. So not enough chemical, whether that be electrolyte or polymer, not enough chemical to the dosing process can also be just as bad as not enough, as too much. So there's a fine balance, and we need to understand that balance with a very narrow operating window for most water treatment factories, to where just enough chemical is added to form a stable flocculant or a coagulant. Now, typically raw water contains many different types of impurities, particularly in the colloidal size range of less than 2 microns. This could be from bacterial things like E. coli, cryptosporidium, to domestic sewage, organic, other types of minerals. And this will vary from not just country to country, but regions within a country itself. Up in the mountains, down in the cities, close to the coast, inland, you will find very different approaches. And this is one of the challenges for the wastewater treatment industry, in that there's no consistent approach. You can't just apply one set of settings to one plant and apply them to another, because the raw water that's coming in to be treated is changing dramatically based around the environment, the geographical location where it is. So typically one of the things that we do is this charge neutralization process to induce flocculation. So ultimately we're trying to flocculate or coagulate all this suspended material to make it bigger and denser so that it sediments and therefore the clean water at the top, or cleaner water at the top, can be taken away for further processing, depending upon the type of plant. And that flocculation process is typically optimized by adding chemicals to neutralize the charge of the particles and induce flocculation. But more chemicals does not always equal better flocculation. And I think this is the key point that we're trying to get across today. So this would be a typical water treatment plant. And of course, this can be different in different places, and more modern plants would be different. But effectively, the water is being taken from somewhere, the abstraction process. This could be collecting the rainwater from the mountains in channels, or from a river or a reservoir. It can then even go into a reservoir, a holding reservoir. But typically, that water is taken into a water treatment plant where chemical dosing takes place, and flocculation happens as a result of that dosing, and it then goes through the rest of that process. So we're removing a lot of the large particles. The cleaner water then goes through all the different sorts of processes that you can see, whether that be UV, chlorination, and so on and so forth. And this first step of chemical dosing or flocculation is really, it's vastly important to the success of the rest of the process. So typically at this point of coagulation, we have our suspended impurities. We add chemicals of some description and at some rate to cause them to flocculate and then to settle for filtration, flotation, whatever that process is, depending upon our plant. Now, the typical tests that are employed by water treatment companies are turbidity. This is a very common measurement in water treatment plants. Effectively, we're looking at the clarity of the water, but it doesn't give us any indication about the charges of the particles, what types of particles they are, and so on. Filterability is another common test. People will take water, they will filter it through different filter membranes or paper filters or whatever they may be, and that will give them an idea of the amount of material they have and so on. Perhaps the most common test, though, is what's known as the jar or the flock test. And we'll talk about that in a moment. But this test, as most people will know on the call today, it's very slow, it's time consuming, it's not really dynamic because it's only representative at a certain point in time. So if you collect your water, by the time you've taken it back, you've done the test, it could be an hour later, could even be 3 hours later, depending. Another area that people have used is streaming current. Streaming current is another way to understand flocculation, coagulation. It has a relatively low sensitivity, and again, it's not specific to charge, so it doesn't give you an idea of what's happening from a chemistry point of view. And then the final tool is Zeta Potential, and this is what we're going to talk about a little bit today. And Zeta Potential is used more and more these days in optimizing flocculation tests, both laboratory or in process real time. It's a very sensitive technique, highly sensitive, gives a strong indication of the particle charge, and is very good at predicting what you need to do in advance based on other things. So it's highly desirable. So let's just have a look at that common jar or flock test. The diagram that you can see down here on the bottom right is probably very familiar to a lot of people, but effectively you take a sample of water and you add to that each of those beakers or jars a certain amount of chemical, whatever your chemical of choice is, or combinations of chemicals. And you mix this for a certain period, and then visually looking at the clarity, some people also measure the clarity as well, you then determine how many milligrams per milliliter of material you have is required to dose accurately. The problem is it takes a long time. It's a very manual process. And the delay between taking samples, getting the results, and acting can be quite long. Streaming current is also used in some places, and what we do here is typically we're measuring the current induced by flow of water that contains these charged particles as they move across a sensor. It can't really determine as a technology between changes in the conductivity of the water and the particle charge. It also depends upon the uniformity of the coating on the walls of the sensor as well, and tends to be affected by fouling. So if the sensors get contaminated over time, you get reduced sensitivity. So it's a very good tool for indicating a major process event in your water treatment plant, but it's not very good at long-term or real-time prediction or control. Zeta Potential. Zeta Potential is a technique that's deployed by a lot of companies, either, as I mentioned before, in a laboratory environment or a process environment. It's an absolute value, which is good. It's reported in millivolts. And it's a very good tool for not just measuring the system charge of the material, your suspension you've got, but also at predicting what will happen if you are to change that chemistry. Okay, it's highly sensitive. Even very, very small changes in water type or content, it gives us all the information on the charge details, so it helps us to understand what kind of chemicals we may need. Highly repeatable, very fast measurement, and obviously can be done with little or no user intervention. Just a small comparison table between streaming current, just to summarize what I've said there, because these are two areas that people assume that Zeta Potential is the same as streaming current because we're measuring charge or and so on, but they are very different. Streaming current typically requires calibration. Certainly the output, you need calibration. We're only measuring a small amount of the particles that absorb onto the walls of the current. The concentration of particles very often gives very low signals, so is one of the reasons why we don't see, or we don't have high sensitivity. And of course, the signal you get will depend upon the conductivity which is present in the sample that you are measuring. Zeta Potential really addresses all of those problems. It doesn't matter what the material is because we're measuring the material directly. All types of particles, organic, doesn't matter. It's an absolute technique, no calibration, which is obviously beneficial. We can also measure at incredibly low concentrations. And I think this is, very interesting. I've been to a lot of water treatment facilities around the world, and some of the water that I've seen that is designed to be treated is as good as the water that comes out of a water treatment plant in some countries. So there are different, things that we need to look at. So let's just remind ourselves, first of all, what is Zeta Potential? So let's have an example of what we mean by dispersion stability. So the stability of a colloidal dispersion of these particles suspended in a liquid is determined by the sum of those attractive forces and those repulsive forces as the particles experience when they interact with each other. The attractive forces are known as the van der Waals forces. The repulsive forces are the electrostatic forces. So as these particles come closer together, they are effectively making a decision. Am I attracted to the other particle or am I repelled from the other particle? My wife likes to think this is the way in which we met. She often refers it to the Zeta Potential. We were attracted to each other and not repelled from each other. Now, the important thing to remember here is that the stability of a dispersion, of this colloidal dispersion, can be lost or gained through different mechanisms. And Zeta Potential is the one thing that helps us understand that chemistry. The Zeta Potential is measured in millivolts, okay? 0 millivolts is typically what you would call the point of maximum instability. Your system will never ever be more unstable. Its ability to flocculate or coagulate is going to be at its highest. Now, the further you move away from 0 millivolts, either positively charged system or a negatively charged system, the more stable your system will be, the less likely it is to flocculate. Now, of course, 99% of industry today is trying to make a colloidal dispersion which doesn't aggregate or flocculate or coagulate. They want a dispersed system. Of course, in the water treatment industry, we want the opposite. We want to flocculate it. So the goal is always to move towards 0 millivolts as a Zeta Potential measurement from your system. So if those particles have a very large negative or positive zeta, they will repel each other and you will have dispersion stability. If those particles or that dispersion has a low Zeta Potential, then there are no forces that are preventing those materials separating or remaining separated, and they will flocculate. Now, typically in a raw water for Zeta potential is about -15 to -20 millivolts. Of course, that's a big variation and depends upon the season and the geographical location. And a typical Zeta potential required for flocculation or to control flocculation is somewhere around about -8 to +3 millivolts. So typically what happens if you have -25 millivolts as the Zeta potential of your untreated water, you would add a certain amount of chemical, aluminium sulfate, a polymer, or whatever it may be, and you would look at the Zeta potential parameter to see if it is going closer and closer to zero. And as I said, ideally, the operating range for a flocculated system is with the Zeta potentials typically between -8 and +3 millivolts. But of course, that can be different. It could be -10 to +10, depending upon your system. So remember, Zeta potential is the overall charge a particle acquires in a particular medium. It is not surface charge or particle charge, okay? So let's imagine we have a particle now with a negatively charged surface. Surrounding that particles will be ions of opposite charge that are stuck to that surface. And this area around the surface of the particle is known as the stern layer. But a little bit further away from the surface of the particle, we have ions of both positive and negative charge. And this area around the particle is known as the slipping plane. And basically what is happening, these ions are making this decision. Do I go to the particle surface or am I repelled? And what we do in a Zeta potential system is we simulate that area. Now, of course, we don't put ions into the water one by one. We can't do that. But what we do is by putting the water in a cell, and a special cell with 2 electrodes, by switching the laser beam switching the current between the 2 electrodes very rapidly and using laser beams to track the direction and the speed of the particle towards that electrode, we can determine this parameter called Zeta potential. Now remember, Zeta potential is can be affected by many things. Changes in pH, which is something that happens constantly in a water treatment process. Conductivity, the concentration, types of salt. Any changes in concentration of a formulating specific component, polymer, surfactant. So you can clearly see that, you know, the pH is changing naturally for raw water because during storms or different seasons. We know that the concentration and type of salts present are changing as well because of that. And we know that we are adding chemicals, electrolytes and polymers, etc., to the water is also going to change the Zeta potential. So based on just those 3 things, it's actually a very powerful tool and parameter to measure to understand your treatment process. So we typically do that in a laboratory environment. We would have a zetasizer, so this would be the instrument. This is the cell we would use, and this is just a schematic. So you have 2 electrodes on the cell. The water is injected into the cell, into the small capillary, and then we switch the electrodes, as you can see here, very rapidly. And using lasers, we can track the direction of the particles to the electrodes, and we can also track the speed, and therefore come out with that Zeta potential parameter. And of course, this is all done seamlessly and automatically for you within the instrument. And typically you might get a result like this. So here's an example of a particular dispersion, and all as we've done here is measure the Zeta potential versus the pH, but each one of these samples has got different amounts of additive in. So one has got 10 millimolar KNO3, 100 and 300. And then all as we've done is take those 3 samples and measure the Zeta potential at different pHs to understand how the Zeta potential would react. And you can clearly see that at the sample with 10 millimolar in it, we are at pH 4.5, say, positively charged, 60 millivolts. So that would be a very stable system. But as we increase the pH, we can see we start to destabilize it. It gets closer and closer towards 0, till eventually we are adding more ions, so many more ions of opposite charge now, that we completely change the system charge from a positively charged system to a negatively charged system. and we start to make it more stable again because we're moving away from zero. So in effect, we've now got a kind of a fingerprint of how our formulation reacts to pH. But of course, you can see if I have a different amount of chemical, a different volume, in this case 100 millimolar, we have a very, very different profile. So it's a balance of formulation between the right amount of chemical at the right pHs to give us the zeta potential numbers that we want. And remember, we want to be somewhere in this area for a zeta potential measurement of water for optimum flocculation. So we talked there about what is zeta potential, and those measurements would be done in a laboratory environment typically. And that is very common. You know, we have literally, there are hundreds and hundreds of systems around the world at water treatment plants where they are using zeta potential to in the laboratory to assist with chemical dosing. But of course, what we want to do in the water treatment industry is to meet that water quality, to reduce those costs while still meeting those regulatory environments. We want to try and go through an automated process. How can we react quicker? How can we monitor this real time so that we don't have big gaps in between where we have perhaps lots of water treated in an unoptimized way? And remember, when we're talking about water treatment, water treatment, we are talking, millions of gallons of liters per day, and so on in water treatment plants. So it's a lot of throughput of water. So coagulation is that critical first step. We know the incoming raw material, which is the water, can change rapidly. We can have an impact on the filtration processes in less than an hour from changes in the raw water. We need to detect rapidly what is happening so that we can treat rapidly. We need to optimize that chemical dose or treatment. We need to have the right manpower to optimize that. Ideally, we want to remove that manpower to automate that process. And that's where we would move into an integration into a kind of a plant control system, a PLC system. And at the same time, you may want to have automatic dose control. You may want to use the zeta potential and say, right, not only will we act upon the chemicals that we have to do, but the actual complete system will be fully automated. Not only will we understand when and how much we need chemical to add, but the system will actually add the chemical as well. And that's where the laboratory Zetasizer system turns into a process system. This is what we call the online Zetasizer, and it stands for WT, which is basically just water treatment. And if we take that same process again, you can see that what we are typically doing is, instead of manually taking a sample of the water after you've added your chemical and then taking it to the laboratory for measurement, what we're actually going to do now is measure real time at this point the zeta potential. And of course, the instrument is all contained within this process box. It's perfectly suitable to go on plant, etc. You've got this human machine interface, this touch screen on the top, and all your parameters are displayed on there. What is the current zeta potential? What is the history of the last 10 results, 5 results, trends, lots of different things. This is all displayed on the system itself. But of course, this can all be transferred to a PLC system, which is the most common approach. Okay. So if we look at setting an operating range, okay, so here we've got on this axis turbidity, and on this axis we've got zeta potential. So we can see that at 0 millivolts, we have the maximum, if you like, clarity from a turbidity perspective, and we know that all our material is going to be flocculated here, etc. But the amount of chemical that we need to use to attain 0 millivolts is probably too much, because if I move a little bit further away from 0 millivolts, you can see that even at kind of -5, we still have the same rate of flocculation. Even if we move towards +3 millivolts, we still have the same levels of flocculation. So in theory, the amount of chemical we need to add is significantly less, because we know we can get the same rate of flocculation at -5 than we do at 0. So we're saving money. And the problem is today in many water treatment plants is that they are using this turbidity number, and it's often very common to put too much chemical in. They overdose. And of course, if you overdose too much, you actually end up not flocculating. And if you don't put enough chemical in, if you underdose, you have a problem. So if you're underdosing, you need to increase the flocculation or the chemical, the coagulant. If you overdose, you need to reduce. So it's about finding this balance. And Zeta Potential is a very sensitive parameter that can do this and do it real time. So let's have a look at some real examples now from industry. So this is a water company in the UK called Severn Trent Water. They cover a very broad geographical area across the north of England and the Midlands. It's a huge area. It probably has a population of about 25 million, 20 million for sure. Vastly different from geography as well. You've got limestone mountains or hills. You've got peat areas, you've got lowland areas close to the sea. So there's a very broad spectrum of water treatment plants and sources. But here, this is taken from their PLC system in their plant. And obviously what they're doing, they are plotting ferric sulfate dosage versus ferric dose versus Zeta Potential. And I think the important thing is here is that, this is a period from the 7th of November to the 11th of November. This is now back in 2014. So this is not necessarily a new technology, but it's becoming more and more important and understood and accepted. But you can see as we increase the amount of ferric sulfate, we start to increase the flocculation rate. And we can see that because the Zeta Potential is increasing. But we don't actually need to have a Zeta Potential that's, right up here. We just need a lower amount. So we're starting now to overdose here. So by reducing the amount of ferric sulfate, you can see almost immediately, we see changes in Zeta Potential. So it's a very sensitive, very accurate way to determine the Zeta Potential in the process. It's very sensitive to plant or changes or intervention by operators, etc. Now, taking the same company again, but this is from a different water treatment plant. This one is from more northern part of the UK, where there's a lot of mountains, etc. And originally, as you can see, that between November 2012 and typically April 2013, so this is the winter season, so there's always a lot of changes in the water quality because you've got lots of storms, lots of rain, runoff from the mountains, etc. And you can see that they were trying to optimize their Zeta Potential parameters or flocculation rate, if you like, between this kind of +3 and -10. And you can see there were some dramatic changes. And effectively what they were doing to be safe, they were always overdosing or using more chemical than they actually needed to. Once they started to implement using Zeta Potential in the laboratory, you can see that they had a better understanding of chemical usage and flocculation capability, and they were able to reduce this down, and they could find that even at these ranges, they were still getting good flocculation, same quality water, etc., but obviously using a lot less chemical. And that can be seen in the following graph, because what they then did, they took an online system at the same time as using an offline system in the lab. Now, the difference between the red and the blue is just simply they were plotting results from the lab system and the online system at the same time, just to see if they could see the same levels of sensitivities. And broadly speaking, everything is the same. So you can see that in 2015, this is going all the way through from May to August. You can see that by adjusting or making these small adjustments to the amount of dosing, they went from kind of -4 as an average to somewhere around about -8, -9 perhaps on a Zeta Potential, yet they were still able to achieve the same levels of flocculation and turbidity, etc. But they had seen a reduction of 3 milligrams per liter in chemical, in this case, the ferric sulfate. Now you think 3 milligrams per liter, that's nothing. Don't forget, you know, this is a typical plant that might be something like 160 million gallons a day. Yeah, so it's an enormous throughput. So these chemicals start to add up quite quickly. Again, if we take this is now from a water treatment plant in the US, in Utah. This is a 160 million gallon per day plant of water. And again, this is just taken from their PLC system. And you can see they have got flow rate across the top they're plotting. They are plotting filtered turbidity, polymer addition, and the Zeta potential, amongst other things. And what this really shows you is that if they start adding more polymer, okay, or in this case, reduce the amount of polymer, you can see that we see this change in Zeta potential. And if they increase it again, we can see the Zeta potential goes back to where it was. Then they make a smaller change of polymer addition, and we detect that smaller change. It's not only has less polymer been added, but the effect on the Zeta potential is not as pronounced as well. So effectively, what they're doing here is that they are adjusting the amount of polymer and using Zeta potential to get into this region of here where they know they've got stable flocculant with a known set of chemicals that if it changes, they can increase or decrease and use Zeta potential as the parameter to understand. So here's another plant. This is another large plant, 80 million gallons a day, but this is a direct filtration facility. Same concept, you know, still chemical dosing, but using a filtration process, a direct filtration process. They typically are looking at dosing between -3 and +3 is their optimal range. They used to measure Zeta potential in the lab, typically once a shift. Now they have moved to an online system and they're typically measuring about 400 to 450 measurements per day. The results match with the online systems very well. And the good thing is all this data is now exchanged with their PLC system and control systems via protocols like Modbus or TCP, SCADA, or whatever. And it is the plant control room that is making the decisions for chemical dosing based on the Zeta potential parameter from the real changes that they are seeing. So here we see an example. Again, this is going from January to May, and you can see that everything is, you know, running okay between online and lab is very good, and you know they've got good connections. And obviously the Zeta potential is moving because the raw water is changing. In this example, however, this is now going into the summer. So this is now going from the May into August area, and you can see they see some big changes. So during the summer months, the levels of chemicals that they need to use are very different from the levels of chemicals that they use in the winter months. You can see the Zeta potential is changing. But the good thing is even though these numbers are much higher and much further away from zero, they are still achieving the same levels of flocculation to allow the plant to operate efficiently and maximize the chemical usage. And this again is taken from their PLC system. So again, on here, you can see that they are looking at conductivity, and the orange line is Zeta potential. And we just also made some arrows here. These are different process events. So they had an analog card on one of the dosing systems failed, so it wasn't dosing correctly. At this point here, the filters started to show an increase in turbidity and blockage. So they added more chemicals and so on and so forth. But the thing to point out on this slide is that if we go from this point to this point here, you can see that typically they would have been adding about 4.1 milligrams per liter of alumina and about 3.05 milligrams per liter of cationic polymer. And by the end of this process event, which I think is over just maybe a 30-day period or perhaps even a bit less, they were able to achieve same levels of flocculation, but with much less alumina, down to 3.65, and polymer down to 2.75. And for those people who are aware of the cost of these chemicals. The cost of the alumina and ferric sulfates is expensive, but in comparison to the polymer, it's extremely cheap. The polymer is very, very expensive in wastewater treatment. These are just some comments from some of those operators. You know, the Zeta Potential provides us with this measurable and reliable value that indicates when we have a production issue is occurring or about to occur. It gives us better sensitivity and a sharper indicator that the process has changed. It helps our operators make informed decisions. And they use this as a proactive tool for preventing treatment problems to keep the plant running smoothly. So there's clearly some good feedback from the operators. And if we look at how that's translates into the business considerations for justifying this, well, clearly they have addressed a technology gap that they had for flocculation or coagulation control. It gives this enablement of unattended operation and automated dosing control so they can utilize manpower better. It gives them this future proofing and preventative. They've clearly got significant savings in chemicals, but they've also got significant savings in sludge as well, if it's a non-direct filter plant. And of course, if you're producing all this sludge in a traditional sedimentation plant, you have to consider the disposal of that sludge as well. So there are also cost savings that can come from that area. And that Velminger plant in the US typically saw about 20% cost savings in chemicals and sludge removal, etc., by moving to online Zeta Potential. Okay, and these are some of the numbers. So in 2010, this is before they had online Zeta, they were typically spending about $70,000 on alumina, about $220,000, $214,000 on polymer. So about $284,000 a year on chemicals to flocculate the water suitable so that we can all drink it and bathe in it and so on. So the cost per million gallons of water was about $32, okay? And they delivered that year about 8,739 million gallons of water. 2011, they implemented Lab Zeta, and immediately you can start to see the cost savings that they are achieving. Okay, we've dropped significantly, particularly in the polymer, and we've gone from $32 per million down to $22. That's a huge cost saving in a water treatment plant. 2012, they implemented the online, and they're able to get the cost down even more. And this is really affected because they're able to do these real-time measurements. They are able to respond so much faster to changes in the plant. 2013, the cost actually went up, and this was affected because they had huge flooding in the area because of the environmental conditions, storms and melt flow from the snow, etc. And of course, they had to use more chemical. Their plant was out of control many occasions. It was changing rapidly during a 1 hour period, never mind a 24-hour period. So they had to use more chemicals to keep it under control and the vast changes. But what they anticipated is that without the Zeta Potential, this number would probably have been up towards $30 again, possibly even higher than $30, because they would have been reacting completely manually on that data and constantly overdosing or underdosing. So even though those costs went up, those cost restrictions meant that they handled those water treatment plant problems, process changes in a very efficient way. There are a lot of things. If you go onto the internet, there's a lot of papers. Again, here's another example this is from Severn Trent Water. You know, this is a whole paper about using the Zeta Potential, and it talks about they've demonstrated it's be a more appropriate method for optimizing coagulation. They've also identified that chemical savings of 22% and generating 10% less sludge, which again has its own costs associated with it. So it's not just one plant, there are other plants as well. Another example in a water treatment plant, this is again a UK plant, but this is a direct filtration plant, not a traditional plant. Typically, it's 40 million gallons to 160 million gallons. And in fact, this plant is actually a hybrid. I'd forgotten about that. This has a mixture of the two filtration processes. These are the chemistry that they're typically using, which is pretty standard. But again, they were able to use the system to save money. So it's very clear that the use of Zeta Potential or online Zeta Potential is a very, very valuable tool in terms of optimizing the dosing process and therefore controlling your chemical cost and potentially sludge production as well. Okay, well, that's it from me. I'd be happy to take any questions if there are any.
Any questions? Actually, someone wrote in the chat that he wanted to ask something. Just a minute. Mandy, was that you? Would you like to ask something? I'm gonna open Mandy's ability to ask question. I'm unmuting you. Hi, Mandy.
Hi, can you hear me now?
Yes.
Oh, excellent. First of all, Stuart, thanks a lot. It was very interesting. In fact, I think I heard some of this presentation in the SWIG webinar a few months ago.
Very possible, yes, very possible.
I wanted to ask you, if I understand correctly, due to the pH sensitivity, it's not applicable to wastewater treatment. Am I correct? Is it only for water treatment that the Zeta Potential can be online measured?
Well, I mean, I guess here this is where we talk about wastewater treatment. Yeah, I mean, there's a lot of people talk about wastewater treatment in the same term as water treatment. I think that the key thing to remember is if you want to use Zeta Potential for wastewater treatment, where typically the pHs are significantly above normal operating levels, you can still do that, of course. But the level, there's no kind of real restrictions on the instrument. You might find that you have to replace the cells a bit more often than you would in a lower Zeta Potential area. So, I mean, the typical feedback at the moment for an online system is most people change the cell twice a month, maybe 3 times a month maximum. And the cells are very cheap, they're pretty much designed to be disposable. But if you are measuring at very high pHs or very low pHs, there is the danger that you will contaminate the electrodes faster. So you may have to replace those cells more often. But that's really only the limitation. The rest of it is just simply chemistry.
Yeah, but my question is whether it's reliable, because in water, you might, usually in raw water, the TDS content and the pH fluctuations would be roughly, it's roughly stable. While treating wastewater, especially if we're talking about hydroxide precipitation or metal precipitation, etc., I would expect that the conditions change so frequently that maybe it's not possible to calibrate the Zeta Potential instrument. Well, is it correct or not?
You would be absolutely correct, and to be fair, that comment would apply whether this was low Zeta Potentials or high Zeta Potentials. It doesn't really matter. What you've got to remember is if the pH is changing, okay, if the rate of change of pH is much slower, let's say it changes plus or minus 1 over a few hours, well, then by default, you are going to have a more stable dispersion. And when I mean stable, I don't mean, flocculated or not. I mean, your system is behaving the same. Okay, it still might be unstable. But if you've got a process or a dispersion where that pH is changing rapidly, well, then, okay, that's what we're trying to understand. You would almost say that it's actually more beneficial to use Zeta Potential in a rapidly changing pH environment because you're trying to bring it more under control. I guess the challenge would be is why is that pH changing so much, and can you do anything about it? Because The Zeta potential measurement could be extremely valid for you, but if you've got no way to control those parameters that are causing the pH changes, then, you know, is it actually worth it? And that's really the challenge. I guess I see, if you go into an aluminium factory, very often they are using a lot of wastewater back in the process, and steel factories and so on. And they see a lot of rapid changes in pH. But those people, or some of those people, they still use Zeta potential as a parameter, but they just know that the pH changes are going to be more rapid. But what they have done is that, and this is becoming quite common now in a lot of big steel factories or aluminium factories, is that in the same way that a water treatment facility would have a reservoir as its holding facility to bring in that raw water, we're finding that more of these aluminium plants now have these big holding tanks where they can control the pH in that area before the water is treated. So that would be one possible solution.
So you have experience in using this online Zeta potential monitoring for the control of coagulation processes in industrial wastewater, or?
Yes, we do. Yes, we do. And of course, it depends upon whatever that industrial process is, and what are the particles in it, and all the rest of it. But the answer is yes, because fundamentally, we're talking about treating water. We're talking about flocculating material suspended in water. What that material is, we don't really care. We only care about it from a chemistry point of view, and so does the customer, because depending upon what chemicals you've got determines what chemicals you use to flocculate. And Zeta potential is merely the measurement parameter. It's a little bit like particle size and milling. You know, it doesn't really matter what the particles are. You know, you can change the mill and you can change the conditions of the mill. The particle size is simply the parameter you're using to monitor the mill. Zeta potential is the same.
Okay. Okay. So, for example, have you got any applications in food industry, for example, dairies or something like that?
Well, Zeta potential and nanoparticle size, because you often find those two things in exactly the same instrument. These are used extensively in food and dairy research for stabilizing. So you will find, particularly in things like food and flavorings, there are many of the big players in these industries. They will have Zeta-sizer systems where they are looking at colloidal suspensions and dispersions, and using both size and Zeta potential as a tool for formulating stability. I mean, that's a common area. In fact, only yesterday the day before, I was having a discussion with somebody in Turkey about using Zeta potential as a tool for understanding protein modification for raw milk. And one of the things he wants to do is, obviously, in a suspension, these proteins will be absorbing onto the surface of the droplets, the fat droplets in the milk. And if you modify the protein, it will then change the behavior as to how it absorbs onto the milk. And effectively, you're changing its binding efficiency. So what that means is that it's potentially, this is a way that you can stabilize the raw milk without having to perhaps use the same level of homogenization.
Yeah.
So, remember, Zeta potential is simply a tool that's used for formulating the dispersion of a colloidal system. Other major application areas are things like printers, printing inks, obviously so many pharmaceutical materials, where you're trying to get dispersed systems and so on. Printing inks, another big area. You know, imagine we have a printer on your desk and it has ink in it and it comes out through a very fine nozzle. If those pigment particles, if they flocculate and get bigger, they don't come out of the nozzle. So what the paint formulator or the pigment formulator does is to formulate a pigment dispersion that's going to be stable and doesn't flocculate. I mean, the only real difference between water treatment or wastewater treatment and everybody else is most people are trying to stabilize the system to stop it flocculating. Water treatment, we're trying to flocculate it.
I think there is, in what you're correct about the water treatment versus the other manufacturing processes. I'm not sure you are correct about wastewater treatment, because the main difference, in my opinion, between wastewater treatment and all the other applications is that the wastewater is not constant. I mean, when you do milk, when you do ink, when you do water treatment, you are more or less in control of the initial state of the media. While in wastewater, it's really not. It changes a lot. Not only the pH, as you mentioned before, but also the conductivity, the salts content. Everything changes out, and this is what I'm asking. Yeah.
Yeah, but you know, to be fair, I mean, you know, to give you a real example, I am based here in Athens at the moment, and if I go to the water treatment facility in the northern part of Athens in the city, if you were to look at the raw water today, you would look at it and think, why the hell do I need to even treat this? It's so clear to begin with. But obviously at a colloidal level, you can't see many of these things. But if I would have gone last week when we had huge snowstorms and so on, that raw water was possibly even 2 pH levels different.
Okay.
Certainly from a clarity point of view, turbidity, it was enormously different. And that's simply because that plant, the water is captured from the mountains that are kind of 20, 30 kilometers from the city. So if you've got these enormous storms, what's happening is that this surface water is coming off into these channels, into the reservoirs. It's changing dramatically. Okay. So even if you go into a water treatment, your raw water source does change a lot. Now, if I go here to Greece, and I would suspect the same in Israel, between probably April and September, October, the quality of the raw water doesn't change at all. It's very good. It's very stable. There's probably few changes to conductivity and pH. In the winter, there are going to be some changes. Not many, but there will be some. If I go to Scotland in the UK, even in the best of times, it would be like the worst of times for Israel, because your raw water is changing so dramatically. And that, you know, in somewhere like Scotland, it probably would simulate something more like a wastewater treatment process.
Okay. And in this and still in these conditions, you can the Zeta sizer works well.
Yeah, it would still work. But what you are likely to see, though, is that the Zeta, you know, in a lot of the examples I've seen, you know, like I said, you're in a relatively controlled environment. So the Zeta potential might be moving around from, you know, let's say +1 to -5, -3, and up and down. What you might find in a wastewater is that variation is a lot bigger and a lot more consistent. But again, without it, it's probably even worse. So you would likely see more variation and less stability overall, because that raw water is changing to begin with.
And if you can just a few words about the cost of the OpEx more is really what I'm interested in. You mentioned that you have to change the cells from time to time, or
so effectively you've got the cost of the instrument and any process integration that you want with PLC systems. You've got all that kind of stuff. If we talk then about operating costs going forward, the only real operating costs are the cells. Okay, because there's no calibrations required. We would obviously recommend that somebody comes along and checks the instrument once a year and
of course,
and does standards on it and so on and so forth, but there's no regular calibration. The only real consumable is the cell. And those cells, I mean, Yale will tell me a bit better because I can never remember, but I think they're, you know, a few $100s for a box of 10 or 20 or something like that. They're very low costs. Now, of course, you know, if you are changing that cell once a day versus once a month, or once an hour versus once a day, there's going to be differences. But you know, you've got to balance that off with what you save in terms of anything else. But still, you know, it is highly demonstrated to a lot of people that using Zeta Potential, even with the associated costs that go with it, such as cells and, you know, service contracts or whatever, it's still insignificant compared to the cost of chemicals.
I'm trying to understand what size of plant is this is this applicable for?
Okay, I mean that's a very interesting question. I think the best way to answer that is not necessarily the size of the plant, but the levels of problems the plant has.
Of course.
So, for example, in I think it was Portugal, there was 2 plants, if I remember. This is going back a few years ago now. But for example, say one plant had about 120 million gallons a day, and the other plant was about 30 million gallons a day. Okay, so quite a big difference between those 2 plants. But what was that? You know, on paper, you would say, maybe the 160 gallons or 120 is the one that's going to see the biggest saving because there's more throughput, more water. But actually, that plant had a relatively stable raw water supply, just because where its water source was coming from. The smaller plant had the biggest variations and was actually using more chemical per million gallons used.
Yeah.
So from a return on investment basis, it was the smaller plant which benefited more than the larger one. And I think that's something to take into account, because if there are some water treatment plants where I go to where the variation across a year is so negligible, a jar or a flood test is going to be more than okay, because you only need to measure it once a day. But if you have got highly changeable raw conditions, or you've got big differences, from summer to winter, or wet season to dry season, then it could be that, okay, well, that's where Zeta Potential comes into its own.
Yeah. Okay. Yes. Thank you very much. Very interesting.
No problem.
Okay, so thank you for all. If you have any more questions, just let me know, and I will let you ask them. Just let me know in the chat. And thank you, Stuart.
No problem. Pleasure as always.
It's our pleasure as well. Yeah.
Okay, thank you. It was very, very interesting for us, and we are also always available here for you whenever it's needed.
Of course, no problem.
Okay.
Then. Thank you.
Bye-bye.
See you all soon, I hope. Take care. Bye-bye. Bye-bye.
Bye.